starting. Thank you everyone for coming to the weekly BHI Colloquium. I wanted to mention that tomorrow we have a new pizza lunch series at the Institute for Theory and Computation, the ITC, about gravitational wave astrophysics. So that's a new frontier that was initiated by the discovery of LIGO, of a binary black hole system last year. And the first speaker is actually Ray Weiss from the LIGO collaboration. It's taking place at 11 a.m., 60 Garden Street at Phillips Auditorium. And there is pizza afterwards, so everyone is invited 11 to 11:45, and then the pizza. So it should take altogether about an hour. If it fits your schedule, you're most welcome. The first talk is by Ray Weiss about this new frontier that just started, giving a broad overview on LIGO, but then there will be additional lectures in the coming weeks on various aspects of gravitational wave astrophysics, so everyone is welcome. Today we have two speakers, and I just wanted to mention that they both come from distant countries. Bülent Kızıltan originally from Turkey, and Tuguldur, or how do you, where is Tuguldur? Here. Sukhbold? Okay. Is from Mongolia, and I should mention your story because you told it very briefly yesterday. I found it quite unusual. So Tuguldur was really interested in astronomy, but there is nobody in Mongolia that does astronomy. So at some point he reached out. Well, he was guided by his parents to study law, but after 2 years of studies of law, he decided the laws of nature are much more interesting. But then he went to the only observatory in Mongolia, and he met the director of that observatory that had a T-shirt that said Arizona on it, because some decades earlier a group of astronomers from Arizona visited that place and gave him this gift, and he thought that Arizona is the best place in the world to do astronomy, and actually some people
second best.
So the advice that Tuguldur got was go to Arizona, that's the best place in the world. So he applied and got admitted. Did you meet him there? Yeah, you know him. And that's how it started, and he started working on evolution of stars with Arnett, and then went on to work with Stan Woosley, where he did his PhD, and now he's a postdoc at Ohio State University. So we'll hear more from him in about half an hour. And perhaps Michael wants to introduce the first speaker.
Yeah, well, so I think it's clear that a priority for the BHI has to be getting T-shirts made and distributed worldwide. Okay, before we kick things off, and welcome everyone, I just wanted to say, we're still in this process of making the Colloquium series, for the rest of this year, but then also planning for the fall and so forth. So if you haven't spoke and you'd like to, especially if you're outside kind of the mainstream astrophysics stuff that we've been doing, please get in touch with me or other Colloquium organizers, or if you'd like to recommend a speaker to invite and so forth. We'd really like to maintain kind of a vibrant Colloquium and also begin drawing on more of the expertise that's not so local. Anyway, so our first speaker today is Bülent Kızıltan. Okay, you got it correctly. And he is a local. He's an associate scientist here at the CFA. And today he's going to tell us about a new technique to study intermediate mass black holes in globular clusters.
Yes. Thank you very much for the invitation. I'm especially pleased to give the first official announcement of our findings and share it with you. It will come out next week in the Journal of Nature. So we wanted to see whether we have something to contribute to the problem of intermediate mass black hole, whether they exist or not, and we think we have something to contribute to the conversation. I wanted to share that with you.
Is the embargo limited to the horizon or not?
Yeah, until next week, only until next week. So the motivation for their existence is obvious from the empirical relationship that we have that we can extend on the M-sigma relationship, which is an empirical correlation of the mass of the bulge and the velocity dispersion. We know they're compactly distributed around here for supermassive black holes and galaxies. A simple extrapolation would give us the globular cluster range, which would predict to have intermediate mass black holes for those clusters. Obviously, for its importance to connect the jigsaw puzzle, that is, connecting the evolutionary paths of stellar mass black holes to supermassive black holes, it's important that we know how they form, where they live, and how they interact with their environment. And the theoretical predictions tell us that globular clusters might be the prime environments where we should really find those intermediate mass black holes. But until now, the observational evidence has been elusive. I mean, it's not been convincing. I will probably hear even people say, well, the observational evidence is really not there, even though they should exist, but we don't see any convincing evidence. So from a theory perspective, on their formation, which is a whole different ball of wax, which I will not go into, is how do intermediate mass black holes form? There are at least 6 or 7 different scenarios which might lead to their formation, anywhere from direct collapse of the first generation of stars to runaway merger, stripped cores of dwarf galaxies, accretion on stellar mass black holes, and a slow build-up. And different scenarios are popping up in the literature, but there are many different theoretical models which can predict the formation of intermediate mass black holes. So in our work, we used different perspectives and tried to merge the information that's at our disposal and see whether we can find a signature, a different way to probe the very cores of globular clusters. So with the use of GPUs, now we are able to create realistic replicas of globular clusters, produce their n-body simulations, and we can input many different types of physics that we already know, and which also has stellar evolution, the dynamics of two-body relaxation, and tidal disruption. And we can run a few hundred thousand stars and see whether we can create realistic replicas. So we will use n-body simulations to gauge the dynamics of globular clusters. So there are different types of approaches to n-body simulations. The full n-body simulation, n-body 6, produces realistic replicas, does the solutions in real time for each individual star, whereas there are some approximate Monte Carlo methods as well. We actually looked at the whole range of different approaches to n-body simulation to see whether it's significant in terms of what we find. The general rule of thumb after we look in all the n-body simulations is the IMBH, intermediate mass black holes, if they exist, they should be preferably exist in globular clusters that are on the more massive side, and the cores are more compact, and we would expect the intermediate mass black holes to form fairly rapidly. So those are the rules of thumbs that we get from n-body simulations. So this range directs us in one particular globular cluster that I will be talking about will be 47 tuc. So again, going back to the empirical relationship that gives us an insight into what types of masses we should expect for intermediate mass black hole, this is the one slope of extrapolation, even though there's some work out there that predicts different slopes for the M-sigma relationship. Basically, assuming that if the globular cluster passing through the galactic disk will lose some mass, the velocity dispersion might flatten a little bit, but again, this doesn't change the expected range for intermediate mass black holes. It should be several thousand solar masses. Yes?
You are extrapolating from normal galaxies.
That's right.
I'll be quite happy if you go down to dwarf galaxies.
Mm-hmm.
But globular clusters are not related to galaxies.
That's correct.
They don't have dark matter.
Mm-hmm.
They are not dwarf galaxies. So why should we expect M-sigma?
That's a very good question. So when it comes to galaxies, I think it wouldn't be a stretch to say the feedback mechanism of the black hole and the galaxy is still not known. So it's just a simple extrapolation that they go all the way down to the globular cluster masses and say if there are
If
masses.
there are, that's okay, yeah,
But nothing
a
beyond
priori
that.
we don't.
Yes,
think they should be
intrinsically we don't know, based on this empirical relationship. But when we look at the N-body simulations, especially the Polish group and the N-body 6 folks, they actually see the formation and the retention of intermediate mass black holes. So this is not the only story. So this is the one that most people are familiar with, and it gives us a broad understanding, expectation what the intermediate mass black hole mass should be. So from an observational perspective, obviously the approach should be to look for an electromagnetic counterpart which would give us an indication whether there's a black hole or not. In the radio, assuming that there is gas at the central cavity, people have looked into it in detail. In summary, there is no electromagnetic counterpart, and based on the non-existence of an electromagnetic counterpart, upper limits have been placed on a putative intermediate mass black hole. So if there is one, based on the lack of radio emission, we could expect them to be below 200 solar masses. From an X-ray perspective, if there is gas and it creates an accretion disk, we should expect to see it in X-rays as well. And based on the lack of the X-rays, also upper limits on the lower end have been placed on the intermediate mass black hole in 47 Tuc. Again, both of them assume that there is gas in the center of 47 Tuc.
How do you get an upper limit from the lack of reactions?
So basically you're assuming a certain geometry for the accretion Bondi hole, and with a certain efficiency you say if there's gas at the center for this amount of mass you're expecting the luminosity to be this much, and based on that,
Bondi accretion.
yes, but Bondi accretion with different types of efficiencies, there's an assumption that goes into the geometry of the accretion. And based on the lack of an electromagnetic counterpart, you can put an upper limit on the mass of the intermediate mass black hole. So from an observational perspective, again, in X-rays, in radio, even in the infrared, you don't see an electromagnetic counterpart. And even in different further away galaxies, there have been some announcement for the ultraluminous X-ray sources, which equally could be explained with X-ray binaries apparently. So there is no conclusive observational evidence that would tell us that there are intermediate mass black holes.
By the way, omega SEM is a good example for our next question because
It's a stripped away.
a stripped
Indeed.
of analysis.
Yes. Yeah. So there are different types of beasts. 47 Tuc is a garden variety globular cluster, but on the more massive side, it's been studied for many decades, so we know really well the global properties of the globular cluster, and within the implications of N-body simulations, it would be the ideal candidate to house an intermediate mass black hole because it's on the more massive side and it's very compact. The core radius is approximately 0.5 parsecs.
Bülent, I have a question. So Sagittarius star, for example, is very sub-Eddington, right? I mean, it doesn't have a bolorimetric luminosity more than, let's say, an X-ray binary or something like that. So if you scale the black hole down, it was also some kind of an ADAF, an advection
Like
dominated accretion flow.
low efficiency
You
accretion.
might not see it also, right? So it's
That's
not just the geometry, but it's also the mode of accretion.
That's
as well,
correct.
right?
So we don't know much about the accretion geometry.
Okay.
So I will get there. So again, looking back at what the predictions are from the theory side, 47 Tuc might be the ideal candidate to look for intermediate mass black holes. So an indirect way of testing whether there is an intermediate mass black hole is to look at the kinematic signature of an intermediate mass black hole. And for this, you have to look for the proper motions and radial velocities of stars and see whether any of those lines fall within the observational points here. So those three different lines correspond to an N-body model with 1% of the total globular cluster mass as a black hole, a smaller black hole in the intermediate mass range, and no black hole at all. So what you can see here, those dots are observational points that correspond to radial velocities and proper motions of stars. As you can see, it really cannot go all the way in because of the crowding of 47 Tuc. In the end, we cannot conclusively say whether any of those models fit better than the other. So kinematic studies, indirect measurements don't give us necessarily conclusive evidence for either or. So 47 Tuc also has 2 dozen or so pulsars, which we can use as probes for the globular properties of the globular clusters. This idea has been around for several decades now. The famous Finney paper lays out the theoretical background of how we can use the acceleration of pulsars to probe the general properties of the globular cluster. Again, this is a rule of thumb. It's a dimensional analysis which gives useful information, but it doesn't necessarily help us to make conclusive statements about the central black hole. We can look in, it turns out that we can use pulsars to look in all the properties of the gas content, the mass distribution, gravitational potential, but really it's notoriously challenging to pin down the central black hole, if there is one. And the data is too sparse to do that, and also the intrinsic spin-down contribution to the acceleration is a source of error which we need to disentangle from the acceleration that's induced by the potential of the globular cluster in order to use this as a source of information to probe the very center of the globular cluster. So we have observational challenges. One of them is what happens if there are primordial binaries? They might act like a black hole. Can we disentangle them both? So what we've done is we've created realistic replicas of 47 Tuc, and what I mean with realistic replicas is we produce n-body simulations with the same surface brightness and velocity dispersion profile, so they have to match, and we use different prescriptions for the primordial binary content. In the end, what we want to see is, does it matter whether you have primordial binaries from the perspective of the neutron star distribution? And what we see here is, for the case of binary and non-binary, they're very close in terms of their total number of neutron stars, whereas an intermediate mass black hole has a significant effect on the distribution of neutron stars within the globular clusters. And I will tell you what this exactly means in the context of using this information to constrain the existence of an intermediate mass black hole. Why? I will tell you.
Not what the result. Why?
Why this is important?
No, not why is it important. Why does it happen? Why does the central black hole affect the distribution of electrons?
Dynamical heating. Basically, if you have a black hole, how it interacts with binaries is very different if you have multiple binaries. It will basically disassemble the binaries.
So it's about the formation, it's not about the mass.
It's during the formation, what happens is the binaries harden and that energy is injected into the close by population, which puffs it up a little bit. So then the problem with the gas, obviously it's overcrowded. Is there gas at the very core? Can we make any conclusive statements about the existence of gas? So our pulsar friends, they looked at the dispersion measure variations within 47 Tuc, and they see evidence for gas that remains within the globular cluster, but this does not tell anything about the central cavity that's within 0.1 parsec. So the dispersion measure is the integrated electron density along the line of sight. So for those pulsars, there's definitely gas, and it's a very small amount, but still we cannot say anything about the central cavity. And then back in the 90s, there was a paper, it's a back-of-the-envelope calculation where you can calculate the RAM pressure produced by, for instance, pulsar. Is it sufficient to clear the gas from the central cavity of globular clusters? And it turns out that almost a dozen pulsars create enough sufficient RAM pressure to clear the central cavity from gas within 1 billion years or so. So without having a continuous enrichment of gas of the central cavity, it would be reasonable to assume, or we'll see later whether there is gas or not, but there is more than one reason to assume that there might not be, in fact, gas at the very core of the globular cluster. So going back to how neutron stars are distributed, so we want to study, we want to see how exactly the intermediate mass black hole's existence affects the distribution of neutron stars. So we have this massive object at the very core of the globular clusters that's steering in, and during the formation, for the reasons that I just mentioned, it interacts with binaries, they merge, and the energy injection really puffs up the population. This is exactly what we see. the first intuitive approach would be, once we look at those two populations of neutron stars, which model has the intermediate mass black hole? I would have said probably this one, because it's a black hole, it would attract the inner population even more, whereas it's exactly the opposite because there's energy injection and dynamical heating due to the existence of a black hole at the very center. So if you have a black hole, the number density of neutron stars really goes up and it's being pushed a little outward. So this will be the other piece of the jigsaw puzzle that we're going to use to constrain the existence and the mass of the black hole.
So the intermediate mass black hole has the same mass at the formation of the globular cluster
No.
as it grows in
It
time?
grows, it's allowed to grow. But the formation mechanism, there are different prescriptions for the N-body models. Especially the Monte Carlo ones, they use different models and see whether it's growing during the formation. In N-body 6, typically you put a star that's massive and see how it evolves. It basically grows as the star evolves due to the interactions.
But Bülent, is that because the neutron stars are in binaries and there's a interaction between the black hole, the massive black hole in the center, and the binaries, and one gets shot out and one goes into the black hole?
That's one part of the puzzle, but that's not the only. It doesn't have to be in the binary to be pushed out. This is due to dynamical friction. Basically, you have the more massive ones that are moving in, and in the case of an intermediate mass black hole, it interacts and pushes all the compact object population. You'll see with the white dwarfs the same way. So they don't have to be essentially in a binary system to be pushed out. So in order to get a real understanding in terms of the gravitational effect, we have to get very close, and we're not able to do that. So we're looking for alternative ways to do that, and looking at the segregation profile is one of them. So this is the actual distribution of stars, the hierarchical segregation of compact objects to low mass stars. As you see, as the stars interact due to equipartition of energy, they will exchange energies, and the more massive ones, due to dynamical friction, will move in, whereas the less massive ones will be pushed out. So this is approximately what the segregation profile would look like for a globular cluster that has an intermediate mass black hole at the very center. And here, there are the segregation profiles for cases with no IMBH. Here, this has the
So
most.
what mass did you use for the IMBH here?
Well, we used a number of.
This particular plot?
This particular plot is for 2,000 solar
2000.
masses. Yeah. So, but we want to see in relative terms what happens if there is an intermediate mass black hole, regardless of the mass, and how it basically reflects relatively to the cases of where we don't have a black hole. So even though the interactions of the stars are stochastic, the segregation profile itself is actually very deterministic. We can calculate it for each mass in the parameter grid. So what we've done is to run different types of N-body simulations and see how this segregation profile changes. And one of the sources of error, as I just mentioned, is the intrinsic spin-down contribution to the acceleration of those millisecond pulsars. I mean, there are different ways one can disentangle the contributions. One can have a very simplistic approach and say, I'm just going to use one value as the spin-down and subtract that from the acceleration term. Or we can look into the evolution of millisecond pulsar and have a probabilistic approach, because we know what the PP dot distribution, the period and spin-down distribution of millisecond pulsars are for the galaxy. And we have no reason to believe that the intrinsic properties of the spin-down are drastically different for millisecond pulsars in globular clusters. So we use what we know from the distribution of the period and spin-down of millisecond pulsars, and use this probabilistically to disentangle the contribution of the mass within the globular cluster from the intrinsic spin-down contribution. So then, what we've done is, so the shaded area represents the acceleration of, the potential acceleration of a particular pulsar. And this is in probabilistic terms. There is a 1 sigma to a 3 sigma range, what the acceleration of the pulsar can be that is due to the globular cluster potential. And what we've done is then look at the same projected distance that a particular pulsar is. Let's say this is at 1 parsec. So in our m-body simulations that are realistic replicas, we have a grid of simulations that have different prescriptions for IMBH masses, with and without. And in the end, what we've done is we've looked at the integrated acceleration profile of those particular neutron stars that remain in the global cluster. So we look at this similar distance neutron star that resembles the observed ones. We looked at the whole acceleration profile and basically make a comparison. So this one is the integrated acceleration profile of neutron stars that have the same projected distance as this pulsar for the IMBH case. And this is the particular signature of the acceleration profile of all neutron stars at that distance with no IMBH. So we created this profile for all pulsars, and we repeated this process for each grid in the parameter space, which means different masses of IMBH, different simulations with and without an IMBH. And in the end, there are different methods which we can use to compare those two distributions. And one interesting method that I came across, have been using for quite a while, that has been underutilized in astronomy at least, is the information entropy or divergence method. Now, there's an interesting story behind that. This actually method has been developed by Solomon, Kullback, and Leibner in the early 50s. Both of them were mathematicians and cryptographers working for the Army and then for the NSA. They basically produced this algorithm, this approach, mathematical approach to measure the differences of distribution, which it triggers down to. They used in cryptography. I don't know how exactly they were using it, but it turns out to be a very useful mathematical tool to disentangle distributions from each other. Basically, it will tell you how likely it is that one particular acceleration in probabilistic term belongs to one distribution as opposed to other. So we calculate the relative likelihoods for all pulsars for each model. In the end, we look at the likelihood of whether there's an IMBH or not. It seems like when we look at the overall likelihood distribution, it seems like having an IMBH is more likely to explain the distribution of accelerations. And what I mean by likely is 10 times more likely.
Why did you use KL divergence instead of the mass of the black hole being a parameter in the model and the maximum?
This is not critical to the outcome. We've done maximum likelihood, we've done Bayesian, but in the Bayesian and
Bayesian,
this is not particularly Bayesian. You can use KL divergence in Bayesian terms.
Correct.
But in Bayesian, you have to have a prior and everything. You don't have to do that. You can use.
Well, you always imply prior. You don't use it, right? When you take that.
Yes, in this one, it's pure mathematical. You can just calculate the difference, which takes into account the higher moments of the distribution. There is no prior assumption in, like in typical Bayesian. So this is not Bayesian.
But I mean, the last step that you wrote there, the DKL proportional to log L.
Yes.
There is an implicit prior assumption there.
Which is?
What your priors are. I mean, the only way to convert the KL divergence to a posterior, Bayesian posterior, just multiply by a prior and that's it. So the
okay.
Philosophically it might be different, but I'm just curious, why did you use that instead of just making?
So in typical maximum likelihood predictions, what the process does is try to optimize the answer that you have, broadly speaking. In this case, there's an extra penalty that goes into looking at the higher moments of the distribution. This is not a metric. So you basically, it turns out that in any type of comparison, you are more certain of your outcome with the divergence method as opposed to a maximum likelihood. But as I said, this is not critical to the outcome. It just gives you an estimation from different perspectives. And as I said, this gives us more certainty in the outcome that we have. So in the end, as I said, I repeated this process for all pulsars, for each point in the parameter grid, for different masses, and in the end, what we see is, it is definitely more likely that there is an IMBH at the very center, and obviously we have to cross-check. We're not relying only on the likelihood, but we have an independent estimation on the total cluster mass as well. This has to make sense as well. Is it consistent with what we observe? And this independent estimate also comes out as consistent with the total global cluster mass. In the end, what we get is this. We find that there is a peak around 2,000 solar mass or so. This is the contour plot that you see for the relative likelihoods. And as I said, we have two independent parameters that have to make sense. We have the intermediate mass black hole with the total cluster mass as well. So in the end, also another way to cross-check whether we find something that makes sense from a statistical perspective is our statistical assertion stable? And we can do that with what's called statistical learning. We can basically sample randomly the number of pulsars and see whether our result converges and is stable. So that seems to be the case, and I will stop here.
Questions?
So obviously, we glossed over the stellar mass black holes. What people might ask, why isn't there a cluster of stellar mass black holes at the center of the galaxy?
Yes. So apparently it turns out that as the stellar mass black holes form, they have to move in through the cluster, and they're being kicked out due to dynamical interactions. But then maybe another thing that I should address is how does this differentiate between dark mass that doesn't have to be essentially a single black hole, but can be an accumulation of stellar mass black holes or neutron stars. The segregation profile looks completely different if you have an accumulation of stellar mass black holes as opposed to a single black hole, because they interact differently with their environments, and as they evolve, it stirs the cluster very differently. So in the primordial black hole distribution, as I showed you, the segregation profile looks very different, even though the content mass might be the same.
If they have stellar masses, why don't they migrate to the outside of the cluster with the low mass stars?
The stellar mass black holes?
Yeah.
Because of dynamical friction, they are expected to move in because they're more massive.
More massive than stars.
It's a co-partition theory, yes.
So when you do your neutron stars, do you give them a whole distribution of masses, or do you give them all
No,
1.4?
it directly comes out of the stellar revolution code that is implemented, and they're approximately 1.4, but not 1.4. It's a distribution.
But who knows how to predict
Right.
the mass? So you're saying it comes out of a...
Yes, there's a prior assumption. It's between 1.2 and 1.6, but there have been lots of work about the distribution of neutron stars. So the typical assumed input for the stellar evolutionary code is once they produce it, they assume it around 1.4 with basically a spread around 1.4.
I was just wondering how much that would matter.
In this context, it
Yeah.
doesn't matter. So we actually tried different
Let
types.
us say half the neutron stars, for some reason, are 1.8
Mhm.
or closer to 2. Maybe they will sink down a bit more and push out some of the others.
Yes, I mean, we check different types of prescriptions for the distribution of neutron stars, bimodal, trimodal,
Yeah.
flat, thick one. Again, the segregation profile looks very different from the case where you have a single IMBH versus multiple stars that are moving in due to dynamical friction. It basically puffs it up, but not as much as an IMBH.
So the fundamental observables here are the pulsars.
The pulsars and the surface brightness and the velocity dispersion of the global cluster.
Okay. So for example, what should be the radioluminosity of this intermediate black hole?
There's no gas zero.
So we don't expect to see it at all. No, I'm saying, what is the expected luminosity?
It depends on the geometry for the accretion that you're expecting. Jay Strader's work basically puts an upper limit. I don't know what the luminosity is for the intermediate mass black hole, and based on that upper limit, he predicts that it should be lower than a certain limit. Are you asking for the exact luminosity in radio?
Well, that depends on the gas content. We don't know that.
Well, and the geometry and the efficiency, there are lots of parameters that go into it.
Okay. So it's interesting that you can hide a 2,000 solar mass black hole.
Yes, in the case where you don't have gas, you can do that. That was the argument.
Well, it's not very different from stellar mass. It can go up to 100.
How about ticks?
Yes.
And this symmetric supernova, right? Because
Yes.
at the time of the formation of the binary of the neutron star, that will change the hardness of the binary.
Yes.
And I can bet that if you change the distribution of the kick, you will make them move left and right.
Yes.
More than
So basically, in the case where we've done different prescriptions, but in the case that we've used, we tried to keep it as simple as possible. We assumed a certain retention rate, like 10% of the neutron stars are retained within the global cluster.
Well, no, it's not about that. It's about changing the hardness of the binary,
Okay.
right? Because if by change adding a kick
Yeah,
velocity, that
yeah.
automatically changes the
Yes.
interest in the hardness of the binary.
Again, with that prescription also we tried different kick distributions, a Boltzmann distribution around 20, 30 kilometers per second, up to 100 kilometers per second, and see how it basically affects the puffing up, which is a dynamical heating. It pushes it up a little bit, but drastically different again. There's no degeneracy. I'm sorry?
500 kilometers per second.
I'm sorry?
500 kilometers per second.
One has to look out.
Because we know neutron stars have like 3,000 kilometers per second.
Yes.
They are leaving the system.
No, I know. So
Yeah,
if
yeah.
there's a whole
I mean-
distribution, then what? Yeah.
Yeah.
The question is those that stay, how
Exactly what
Yeah,
Alan
yeah.
said. So you're
So we're-
comparing it to the scale.
Those are the
velocities
reti-
and the-
Retained.
the escape velocity is 20 or
Sure.
Yeah, ultimately, I think the likelihoods in the acceleration with and without the intermediate mass black holes the differences seem pretty small. So-
With the segregation profile?
Yeah. So there are quite a few,
This one?
no, the one where you showed all the data.
You mean, okay, I know. It is very significant in the end when you basically add all the
Yeah.
likelihoods.
But I think a lot of small changes in the binary evolution or stellar evolution could probably give rise to changes that are larger than those differences.
Perfectly possible, but we don't think it will basically give us a very strong signal like this. And then, in the end, again, we're getting a intermediate mass black hole and an independent estimate for the global cluster total mass that is consistent with what we observe. So it gives us the cross checks that is meaningful.
Okay, I think in the interest of time we should move on, but let's thank you again.
There you go. You want this? That has a laser, but you won't be able to use it. Do you want full screen?
You know what those 30 minutes, maybe a 5-minute warning if you want.
How do you full screen preview?
Okay, so Avi's already given a brief introduction to our next speaker, T. Sukhbold, who's visiting, he's a postdoc at Ohio State, and he'll be telling us about the probability for stars to become black holes.
Alright, so I want to make sure up front that this topic is really broad, but I'm not going to be really talking about all of the possibilities of life synthesis of massive stars, in particular the very extreme cases that go through pulsational pair instability or relativistic instabilities, or in the other extreme, the smallest massive star that dies electron capture supernova. So I'm not going to talk about those guys. What I'm going to instead focus on is basically the most common sort of this massive stars with solar metallicity as an initial composition, and all population one with initial masses roughly between 10 and 100 solar masses. And a lot of this work is mostly based on my thesis work. I just graduated last summer. So I did my thesis with Professor Stan Woodsley at Santa Cruz and co-student Justin Brown, and we closely collaborated with Thomas Janka at Max Planck Institute in Germany and his student Thomas Ertl. And I was a postdoc at Ohio State. I'm also closely working on top. Alright, so we all know that the stars are all the main baryonic building blocks of the universe. And because of this top-heavy nature of the IMF, we have so many small stars and just very few massive stars. However, despite their numbers, they play disproportionately important roles in the galactic chemical and dynamical evolution of the galaxies. So they stir up the interstellar medium, they're responsible for much of the nucleosynthesis that we observe in the universe, and they of course create neutron stars and black holes. And despite their central role in various astrophysical phenomena, we still have big gaps in our understanding of how they live and die. And if you ask me just to list the three most important things, I would list three. Basically, we don't quite understand how the material mixes, especially at the boundaries of the convective regions as the star evolves. And we also don't quite understand how the mass is actually lost especially when the star becomes a red supergiant and pops up. And even for the people don't quite fully agree on how even common massive stars actually explode. So the explosion mechanism is still sort of an open problem still. So a lot of our work revolves around this newly emerging idea, which we call islands of explosions, just to demonstrate that here I'm plotting the mass space increasing this way, and here at the bottom you have 8 solar masses, where basically that's the smallest massive star that you can explode. Okay, so there's historically sort of a conventional notion that basically said if you go up in mass, the difficulty of explosion becomes harder and harder, and eventually reach a point somewhere around 20 solar masses where you can't explode anything above it. It just becomes impossible. So all these stars between 8 and 20 would essentially explode, create neutron stars, and then everything above 20 would implode, become black holes. And instead, this new idea that we're trying to push is basically saying maybe the reality is not so simple. And of course, you would agree at the smallest end that these guys will explode, but as you go up in mass, this actually becomes more and more uncertain. So that there's not just single mass dividing explosions from implosions, you would have explosions in a mass range where you previously thought nothing explodes. And on the other hand, also, you have implosions in a mass range where you previously thought nothing actually implodes. And the reason why we say this might be the case is because the difficulty of explosion in any massive star in general is related to the core structure at the pre-supernova stage, that is the stage right before its collapse. Okay, and we know that people kind of knew for a long time that that structure doesn't vary nicely monotonically with initial mass, and it has a complicated function, and that's why we should expect a complicated picture. And even though this was something kind of known, but people didn't quite fully understand how massive stars evolved to create this non-monotonic core structure as a function of initial mass, and what kind of explosion outcomes you would expect from that kind of scenario. And this is basically where our work comes in.
Is it obvious that the mass is the only relevant parameter?
Oh, well, it's a mass and composition, but I'm just taking like in the simplest sense.
It's not just
to give you
composition,
an
it's
idea.
also rotation.
Yes, the
And
rotation
then
and the input physics too, yes. But mass is by far the most important parameter. Alright, just a quick background on how these massive stars evolve. So what I'm showing is what's called a Kippenheim diagram, or the convection plot, which basically show how the structure of the star evolves as a function of time. Okay, so on the y-axis you have the center of the star here, surface there, it's showing in the mass coordinates. And as a time, the star is born here, the star dies here, and the time scales show actually the nuclear burning time scales of different fuels. And the shaded regions are where fuel burns in a convective episode, and different colors denote the different fuels.
What's the mass of the star you're assuming?
So this would be somewhat representative of a 15 solar mass star. Okay, but as I'll say in a moment, as you change the mass and composition, this will change drastically, especially the inner part. So notice that the star spends most of its life on the main sequence burning hydrogen, and the structure is relatively simple. You have a big convective core episode embedded in a big radiative envelope. But as the hydrogen ends in the core, hydrogen starts to ignite in the shell, and after hydrogen you start going helium, and so on. You eventually go until you form inert iron core in the center. And notice the structures are quite simple when for hydrogen helium were in the sense that you would have a big convective episode followed by a shell burning. But as you go to starting from carbon burning, that's not the case, right? So instead of this big convective episode, you can have multiple shells, and even what I'm showing you right now is not abnormal. So depending on the mass and composition, what kind of mass and composition you attain at this stage of the evolution, the very last part of the evolution could be drastically different. You could have multiple more shells or fewer shells. Some burning episodes could be radiative instead of convective, and some of the shells could merge and split. And in a sense, this kind of the complicated picture that we have in this very final part of the evolution, in the very inner part of the star, is what really is dominantly responsible to create that non-monotonic core structure that we see at the time of pre-supernova. And notice that the nuclear burning timescales drastically decrease starting with carbon burning, and that's because the neutrino luminosities become dominant source in the energy balance. And here I'm showing the log of the neutrino luminosity roughly corresponding in the evolutionary stages, and you see that the log increases drastically starting from carbon burning, and that's because this whole part is called the advanced stages, and the whole point of star burning fuel is to fight gravity, but once the neutrinos take away all of their energy, the star needs to burn faster and more extremely. And one final comment I want to make about the pre-supernova evolution is that when the star starts burning helium in the core, its envelope puffs up and becomes what's called a red supergiant. So transitions from this compact blue main sequence star into a big extended puffed up red supergiant. So when it does that, the whole envelope becomes so big that the information doesn't travel very efficiently in it. So the whole evolution, it's really important for the explodability, which happens in the very center, actually happens so quickly, and that the envelope doesn't really fill it. So this is part of the reason why we can't tell when a bilge is going to explode, because we see something on the surface. There's no easy way of telling where exactly happening inside the interior of the core.
No, this is also complicated by mass loss, right?
Yes,
Or
yes.
binary companion.
Yes, sure. So I actually depicted a little bit of mass loss here. So in most cases of mass loss, the envelope stays in the star, even if you invoke binaries. But if there are some big stars that can lose all of the envelopes, then it's different. But for the most part, you still have an envelope, which will be very big, very extended, and this part of information from this part will have a hard time traveling quickly to the surface. So now we're kind of zooming on this part right before its explosion. So then what you're going to have is
Can I ask one? I'm sorry. I just want to have one more question. Can you go back? So you go from 10 to the 7 years to days.
Right.
That's a huge dynamic range in time scale.
Exactly. So this part of the evolution really happens a few days before its death. So I'm kind of really zooming in the very final stages.
I had never really appreciated that. I'm sorry, I didn't mean to bore
It's
you
okay.
with my revelations, but that's extraordinary. And now I can see why it's so complicated.
Right. And then people used to say we need to publish papers on the silicon burning time scale. So
That was
The neutron star itself is seconds. Damage.
yeah. So the collapse, right? So right before this collapse, you have an iron core surrounded by silicon burning shell, which keeps dumping material. And once the iron core grows in size and eventually exceeds the effective general secular mass, it starts to collapse, and the collapse will actually be accelerated. And it will be so fast that in fastest parts it will actually exceed a quarter of a speed of light, and the whole thing will just happen in a dynamical time scale, which at these craziest densities is only a fraction of a second. But eventually, as the collapse goes on, at the very center, it will eventually reach nuclear densities, and a very powerful sound wave will form in the center, and the whole collapsing force will just bounce up. And historically, for a long time, people thought that this bounce of this, as you reach nuclear density, is what explodes the star. Once the collapse bounces out. Now we know for a fact that's not the case, because as the shock wave goes out, it very efficiently loses energy, mostly in neutrino losses. So in fact, it only travels a few hundred kilometers, and it kind of stalls because it lost all of its energy. However, we of course see the stars exploding in the universe. So basically, the problem of core collapse supernova is really just you have to revive this stalled shock one way or another, okay, to explode a star. And the leading idea in this field is what's called the neutrino-driven mechanism. And if you just look at the energetics, the amount of energy that you release from the collapse of the iron core to a neutron star is truly enormous. It's on the order of 10 to the 53 ergs, which almost exclusively comes out in neutrinos. However, when you look at the typical stellar explosions and you measure the kinetic energies of the ejected material, the amount of energy is only 10 to the 51 ergs. So this model is really asking, yes, neutrinos very weakly couple with matter, but just give me 1% of your energy budget, and you revive the stalled shock and explode a star. Okay, so the consensus as of today, there are a lot of groups around the world do very complicated work to understand this, and the consensus is such that they agree on how the smallest mass stars explode this way. They just go up in mass a little bit, and they get into trouble. So the problem is very much open. All right, and once the shockwave goes out, you see this exciting fireworks, which you call the light curves of the supernova explosion. There are many ways they can be powered. Okay, so I'm just going to mention the two that are relevant for this talk. So there really depends on what kind of envelope you have. So if you have envelope like a typical massive star, like a red supergiant, where you have this extended envelope, if you have that kind of structure in your pre-supernova star, then when the shockwave goes out, it deposits a lot of energy in the hydrogen envelope, in that diffuse matter, so by ionizing it. Okay, and so when the explosion goes on, basically the ejected material releases the shock deposited energy and creates a light curve, which we call type 2p, which is this kind of simple shape, and showing the luminosity as a function of time. So you can see that it has three simple segments. The first segment, when the shock wave goes out of the star, and once the ejector expands and cools, that ionized material starts to recombine, and the luminosity stays roughly constant for about 3 months. So the P stands really for this plateau phase when the luminosity is roughly constant. And once the recombination ends, the luminosity drops down, and this tail section is dominantly powered by the radioactive material synthesized by the explosion, which is another form of shock deposited energy. But now, when you have a progenitor star that doesn't have any envelope, so you imagine a star that had experienced a lot of mass loss and lost all of its envelope, or imagine a binary where it sucked, the companion sucked up all of its envelope from the other star, then, because you don't have this hydrogen envelope, you don't have this plateau phase. Instead, the light curve is very simple, kind of bell shape. Notice the difference in the time scale. It just peaks out in 3 weeks and then dies down. And the whole thing is just powered by radioactivity. All right, so I mentioned that people kind of knew that the final density structure is what determines the explodability. So just to demonstrate that, here I'm plotting the density profiles in the very inner part of the star for different models of different initial masses. Okay, so the smallest star that you see is like 9 solar mass star. If you look at the density profile, it drops down in the center very quickly outside the iron core. But if you go up to look at the higher mass star, it doesn't drop off. It actually stays very high for a much further mass. And people just, without knowing anything about the explosion, they just concluded that easily that no matter what you invoke in terms of explosion, these stars have to be easier to explode because densities drops down so quickly, there's so much less ramp pressure that you have to overcome whenever you try to explode these guys. And one way of characterizing this is what's called the compactness parameter, which is really just the inverse of the radius enclosing a certain amount of mass. Okay, the mass is usually taken as 2.5 solar mass, so that it encloses the iron core and some of the surrounding materials. Just one way of sampling this density structure. Okay, and in terms of explodability, you can see that when the profile is very shallow, you have to go far in radius. So when R is big, the parameter is small, it's easy to explode. And the other way around, when the profile is very extended, the parameter is big and it's hard to explode. So we run 200 models with initial masses between 9 and 120, all the way from its birth all the way to its death. And we basically calculate this parameter as a function of the initial mass, and we get a picture like this. Okay, so all these points are sampling the density profiles of all of these stars right before its collapse. And you see that it's not a simple function of the initial mass. Instead, it shows these complicated behaviors. And so the question of why that we expect stars to have not a single mass differentiating explosions from implosions is really hidden in this figure. Basically, if you understand why these curves appeared here, why this has this specific function, then you would understand that. And there are a lot of interesting physics at play here, and some of which are a little bit easier to understand. For example, for this highest mass stars, these are the stars that experience most mass loss. So they lose so much mass that they end up with a core structure like a smaller mass star. But then there are the physics that play responsible for this more interesting part with these peaks and gaps. That's more related to the details in the advanced stage evolution, specifically how the shell burning of one fuel dictates the core burning of the next fuel. So depending on the location of the shell burning episode, the core burning episode could be bigger and smaller, and that drives these humps and peaks. And once we thought we kind of understood how this varies, we were first very skeptical. How do we know this is a real thing? So we went on to do a very extensive set of tests, considering the uncertainties in the inputs of the stellar evolution. For example, convection physics, nuclear physics. Mm-hmm.
Just to take that one very big peak, it's a full factor of 3 difference.
Right.
So what's going on? What's the physics?
Well, the physics is because the oxygen shell for these stars, as you go up in mass, it just sets up at higher and higher location. And once it sets up at higher location, the next fuel, which is silicon, burns in the core, right? Has to follow it. But once it sets to high enough location, actually, when it passes the effective Chandrasekhar mass, the silicon doesn't have to wait for the oxygen to finish burning. So it actually starts burning earlier. But when you burn earlier, the silicon burns effectively as a small core, because the above burning oxygen relieves its pressure. So when you start to burn as a small core, the size shrinks. So when the size shrinks, the compactness goes down. But eventually the oxygen shell keeps going up and stops bothering how the silicon should burn after it. So and then it grows up again. But by the time we want to grow up, the mass loss is so strong that it actually doesn't grow, it stays low.
So this 2.5 threshold in those models, is it above the oxygen or below the oxygen?
It's right. So it depends on the model, it depends on the initial mass, but for these guys, it's like right encompassing.
I see.
But if you chose instead of 2.5, you chose something else.
Yeah, you saw something else,
Then you
then of
get
course
different
these values will change, but
Yeah.
this general structure will be robust. And not only, so this 2.5 is nothing magical, it's just one way. You can do it many other ways. And this structure is not only robust in how you define that parameter, but also it's very robust against the uncertainties in stellar physics. And we also did the resolution test. We repeated the whole exercise with another code. And the main conclusion is that the exact location of the point with respect to its initial mass is uncertain. You change the input physics, that moves around a little bit, but this general variability is extremely robust. So once we thought that we understood why the core structures are non-monotonic, we set out to ask what kind of explosion results we would get. So to explain the way we did, I'm going to briefly mention how people used to do these explosions, okay, the survey of explosions of a bunch of different stars. So the way you do is basically the old way was just take a pre-supernova model, the center here, surface here, and you basically have this magical knob where you can move it around and you can pick a point where you say, okay, everything inward is going to become a neutron star, so you're indirectly determining how big the neutron star is going to be, and then you dial in an energy on the piston located on this location. So then you decide what kind of energetics of this exploding ejecta material. So you indirectly decide what kind of nucleosynthesis this will experience and what kind of ejecta energies it will have at late times. All right, now this time we said we're not going to do it that way, and we did it first time in a very completely different way. So to explain that, we took basically two supernova data where we have some handle on the explosion energy and the amount of heavy material that was created. So the supernova 87A and the Crab supernova, supernova 1054. And then we take several pre-supernova models that are representative for these two cases. Okay, we take in the same way we take a few pre-supernova models, and then we also pick a point. But we pick a point that's for sure going to end up in a compact remnant. We pick a point here about 1.1 solar masses, because the neutron stars are bigger than that. So we know pick a point that's everything inside of it, which is going to for sure going to end up as in a compact remnant, and we replace it this inner boundary with the analytical model that describes how this contraction of the iron core to the paraneutron star evolves. And basically the idea is that this inner boundary contracts, emits its binding energy neutrinos, and then those neutrinos mingle with the ejecta material, and we calculate that through neutrino transport, and then the star tries to explode. So there's some tuning involved in the way we represent the contraction up to the paraneutron star, and we've basically tuned those up with using these two supernovae. And now the key is that once we have these tuned up models, we record how the history of this inner boundary moves in time, and then we plant them inside all the 200 models, and then we just sit back. Okay, so we don't tell how each model going to explode. We just plant these tuned contraction histories inside, and then we just let it go. And when you do that, you kind of get three possible outcomes. The star can explode and create a neutron star, or the other way, star can totally implode and become a black hole. Or of course, there's a solution in the middle where some of the star explodes, but you experience a lot of fallback and you actually create a black hole with the supernova. So when you do that within those 200 models, this is sort of the answer it gets. So this is the initial mass on the x-axis. So every vertical line is a successful explosion that's creating a neutron star. Every vertical black line is an implosion. And if you look carefully, there's some fallback explosions here. Okay, so you notice that there's no single mass that differentiates the explosions from implosions. Instead, you get this much more complicated picture when you make the explosion dependent on the core structure.
What happens in the white area?
So in the white area, it just shows that we didn't have a model, so the mass spacing wasn't even. We had too many models here, but not many models here, because we didn't expect many models here to actually explode.
Is it fair to say that because of your particular choice of this C2.5, these numbers could move around, and that particular cut makes you potentially sensitive to numerical uncertainty? So maybe the some of those islands are numerical, but the overall picture of
That's for sure. Yes, all I'm trying to advocate is just overall picture. Exactly.
Overall picture is definitely these islands, but
Yes.
you wouldn't, for example, say that
The really narrow ones. Yeah.
So at around maybe 70 solar masses.
Yes.
That you don't believe it to
Yeah,
that.
so I don't
scale.
believe in that to that
Yeah.
level. Yes, absolutely right. So now we take all the successful explosions, look at their explosion energies and the amount of heavy stuff produced, and when we plot the correlations, this beautifully matches with the actual observed measurements. And when we look at the light curves, again, we've taken all the successful explosions that created the type 2P light curves, where the progenitor had some amount of envelope, and this kind of a spaghetti plot showing all of the outcomes together. And you can see that the range of the luminosities on the plateau phase and the duration of the plateau, they also beautifully match with the observations. And then we look at the distribution of the compact random. So for this guy, we basically take all of these explosions and integrate over the Salpeter IMF. And here's the neutron star distribution. The different color bars are our results, and the dashed distribution is kind of what we get. It's actually from Ozel and Fear, and it's kind of a representative of what kind of distribution we have as in the observations. So of course it's not a perfect fit, but we get first time this nice spread, which kind of nicely resembles what we see there. And for the black holes, and they're slightly complicated because we don't know how exactly a star implodes. So the traditional people thought that the pre-supernova star just becomes a black hole, but now there is some theoretical evidence saying that actually some of the envelope material gets ejected. Okay, so since we don't know how much of the envelope gets ejected, we just take the two extremes, where in one we say, okay, all of the envelope is ejected, only the helium core of the pre-supernova star collapses. Then we get a distribution of the black holes, kind of peaked at lower mass, but on the other extreme, when we put in all of the envelope mass into the collapse, then we get this blue distribution at higher mass.
Why don't you get black holes below 4 solar masses?
Because, so the very big neutron stars are very small black holes. They're dominantly formed by the fallback supernovae. And if you notice in the previous plot, fallbacks are super rare. So, but again, remember, these are all solar metallicity models. So in the solar metallicity models, we do explosions this way. We don't get many fallback supernovae. So we don't get any small black holes. So of course, the first LIGO detection black holes were really crazy massive. So I don't think the stars that I'm talking about now are responsible for them. But the second detection was very nice. They had the 7 and 14 solar mass, which falls nicely on this green distribution. All right, now we do the same thing for the nucleosynthesis, where we take the explosion outcomes, integrate over the IMF. So the way it's now shown is all normalized to oxygen and compared to solar as a function of the atomic number. So this yellow band is basically what we see in the sun, and ideally we want to have all points lying in it. But of course, massive stars are not responsible for all of the elements in the universe, so we don't worry about some of these deviations. For example, the smallest elements are created by Big Bang nucleosynthesis, and there's some elements off axis like beryllium created by cosmic ray spallation, but things like that we don't worry. And you notice there's some nice agreement around here, and then there's another dip here. And actually, we don't worry about this dip too, because it's what's called the iron group. And we don't worry because most of the iron in the universe is created by the thermonuclear explosions of white dwarfs instead of massive stars. So we don't worry about those. But we really worry about this dip. Okay, so this is called a group of elements, so-called the weak component of the S-process elements. And we know almost for sure that the massive stars are responsible for these. And it's a direct consequence of us giving up the luxury of exploding any star any way we want. So in the previous studies, because you could basically tune those things, we could nicely match it up. But now once we give up that luxury, we have this serious deficiency. Right, so there are sort of two ways of trying to go fix this. One is just maybe the reaction rates are wrong. Maybe the star should produce more of these. And we did some offline calculations on that, and it doesn't look very promising. But the other interesting way is maybe the way we represent the explosions is not the full picture with the neutrino-driven mechanism. Maybe there's more. Maybe just stars should explode a little bit more often. And so with Todd Thompson and Heist, we're revisiting an old idea about rotational powered explosions, and we look into the history. The first paper they discussed actually came out in 1971. It's literally right after the discovery of the pulsar. However, even though people have been talking about it for a long time ago, the idea didn't become famous. I think it's because of the success of this point explosions in red supergiants, but it kind of got resurrected very recently as a viable engine for the most energetic explosions in the universe, for gamma ray bursts and superluminous supernovae. So here I'm showing a plot of different types of light curves that we see in the universe, and all the light curves that I talked that emerged from typical explosions I talked up until this point, they're all around here. So there are a whole class of very bright supernova light curves where they just represent a very energetic, powerful explosions. And it's still an open problem, but one of the most viable source engines is what's called the millisecond magnetar. So the idea is when the star collapses, the core becomes a very fast spinning, very pulsar with a very high magnetic field, and it gives away its rotational kinetic energy to power the ejector and make the light curves very bright. And imagine this bar represents the energetics of all kinds of explosions we see in the universe. Okay, so the most powerful explosions are more blue, least powerful are more green. So we know almost for sure that the things that lie on this end, like gamma ray bursts and superluminous supernovae, they're almost exclusively powered by rotation. And on the other end, we know that some of the least explosive, least energetic explosions are powered by neutrinos. Then if the nature really works between these two extremes, then there must be some things where they're partially powered by neutrinos and partially powered by rotations. And so with Todd, we're basically asking, can you actually make normal supernovae with the combination of the two? So the way we go on, do I have time? 5 minutes? Okay. So the way we do just the simple toy experiments, where here I'm showing a light curve plot, and this band is basically what represents all of the typical type 2p supernovae that are ever observed. Okay, you can put in all the type 2p supernovae that you ever observed, and they will all lie in this band. So then take a typical progenitor that we expect to create this ordinary type 2p supernova, and we first explode it with a very weak piston, representing a very weak neutrino-driven explosion. And if you don't do anything else, you get a light curve like this dashed curve. Because you give so much little energy, you don't ionize, you don't deposit enough energy in the envelope, so the plateau is very dim, and because the ejecta is moving very slow, the plateau stays very long. So it's very different than the typical thing you see. However, in the test we're doing, basically we initiate explosion like this, but then we turn on a magnetar. Basically it decays away its rotational kinetic energy through a dipole emission, and turns out we can actually create light curves that are almost impossible to distinguish from typical type 2p you observe that you expect coming from the point explosions. And you notice that the plateau phase is not just constant, there's actually some diversity, and it turns out it's a very good thing, because the other way of interpreting these explosions, they had a very hard time explaining these diversities, and this is what actually observed. But in the magnetar scenario, this just comes out naturally. All right, just to sum up, the main points of this talk was really that
Those magnetar models, they were still spherical?
Yes. This is a super toy, one-dimensional spherical
You don't
symmetric
expect it
calculation.
to be a spherical
Yes,
system.
yes, of course. So we're basically looking at least energetics, and those kind of details don't really matter much when you're looking at this broad light curve properties. So the main conclusion from this talk is that the pre-supernova core structure is, we think, really robustly non-monotonic with initial mass. And when you make the explosions that dependent on this non-monotonic core structure, we get lots of good results that resemble the observations very well, except the nucleosynthesis. But it seems like there's a way to fix this without breaking all the good part by invoking rotational energy source. And in the end, like any good scientist, I want to honestly admit that even though I've been advocating this kind of picture against this, there's no clear direct evidence of it. However, people started to do some very interesting work very recently where, for example, one group of people look at a supernova, go back to old image, they actually see the progenitor star, and they can get some idea on the initial mass. And when people do that, this is the mass range they get from all the supernova explosions. So this is all lie between 8 and 20 solar masses. So you see that this agrees with both of them. It doesn't support or disprove any of them. And then there's other group of people where they look for disappearing stars. And they've been looking for many years, actually 2 years at the highest state, and they very recently, a few months ago, found their first candidate, and the mass was around 24, 25, which is again, points out, agrees with both interpretations, but it's really exciting that people can do this kind of things now, where they can, instead of this nucleosynthesis yields or the light curves, very indirect evidence, they can actually directly test these kind of theories. So, for example, if these guys find a supernova explosion from a progenitor with mass around here, that would be very nice. Or if these guys find a disappearing star with the mass around here, then that would be very nice. Alright, I'll end by saying that all of my calculations are fully available if anybody's interested in this kind of work, or just use these models to do something else. I'll be more than happy to work with it. Thank you.
When you saw the nucleosynthetic yield difference at the high end, it seemed that it was not a normalization difference, but a spectral difference, right? It evolved with atomic number.
Yes.
So it's not really, if you take face value, it's not really a question of number of supernovae, but it's the yield that you get from the particular supernova. Are these S process?
A weak S process.
So,
yes.
if I were to just close my eyes and say, it seems that the location in the supernova where you make the S process in the density temperature diagram just needs to be offset, which most likely you can do by changing the equation of state of the protoneutron star and move that around.
So the S process is not really dependent on the. So I don't see why you say you can change the equation of state of the neutron star.
Just changing the profile. By changing where the protoneutron star lives, you change the density temperature profile of the entire envelope.
So the S process, the elements that are deficient actually formed before the collapse. They're formed in the shell helium burning.
True.
So it's not really affected by the way the explosion happens. So I think the things that would be mattered are like our process elements if these stars are responsible for that. So.
Correct.
So
Just
for
in-
that,
It's just in the evolution, but
Right,
but
in the
supernova
evolution, exactly.
that you need to change the
Yes.
shell burning properties
Yes.
in order to make that happen.
yes. But again, the only way you put out the elements in the space is if you explode, right? You can create a lot of things when you're alive, but when you die, you just collapse the black hole. You don't contribute.
So one of the mechanisms that people keep talking about for supernovae is kind of convective overturn and SASI and all of these instabilities and
Right.
stuff. You haven't included that, right? You're
This
only
is
looking at the
yes,
neutrinos.
exactly. So we want to understand this
Sure.
whole properties of
Mhm.
all kinds of different stars, and
Right.
look at this global picture, right? So
But I was wondering, could you just very briefly tell us, what is the status of those ideas? Are they still alive?
yeah, they're still very much alive. There are all these big groups around the world. They're doing the three-dimensional, this
Right.
so-called ab initio, the first principle calculations. They're all doing that.
Would change
But-
the structure of the star.
Exactly, yes.
But SASI in its initial conception is not alive anymore.
What do you mean?
The fact that the explosion itself is due to the sloshing,
Oh,
this
yes, yes.
asymmetric.
Oh,
that-
no,
that-
yes, yes. So
Yeah,
that's
But
that's
the
a
question
very
is
old
what
idea.
happens if you
Yeah.
mix the layers that
Right.
you assume they are
Exactly, yeah.
isolated.
Sounds spherical.
But actually, when you look at some supernova, there is evidence for mixing, right? Based on the fact that you have material that was supposed to be deep in the core,
Right.
comes
But,
first.
but it's very weird, it's the iron that's ahead of the silicon,
Yeah, that's
right.
my
How
point.
do you get that?
So
Well,
my point
it's
is-
What kind
it's
of
a
mixing will
right.
give you that?
It's that's a.
well, if you have tons of things, I mean, if
So
there
the-
is
You would- yeah,
At
you
the
would
early
have
time
to-
of the ejector, right after the explosion, they're like naturally unstable to really tell
Right,
it, for example, right? So when you do this multi-dimensional simulation of the ejector, we just see the mixing clearly.
but that will not affect your conclusions.
Not too much, not too much. Yeah, as long as the star explodes, everything comes out. So when we do these yields, we're not just looking at shells of ejected material, we're looking at everything that was ever put out into space.
We are violating this standard paradigm that says that theories always believe their models.
Well, yeah.
We are arguing from a theoretical point of view that one should not believe the model.
Right.
And
Only
that,
because it's not our
yeah.
model.
But again, so the way the mixing is done, so my models have mixing too, but in a 1D scenario, you can't really effectively simulate, for example, really Taylor instability, right? So the way we do is there's some observational criterion on how the ejector mixed in the supernova 87A ejector, so there's some tuning involved in that. So actually in the 1D setting, the way it's done is just you run a boxcar several times until you see the kind of desired tuned material that you see in the 87As.
I didn't finish the sentence, by the way. It says that the theorist is the only person who believes his model. Everyone else doesn't. And then an observer is the only person that doubts his data. Everyone else believes his
Yeah.
result.
I mean, I think that's true.
Okay, with that, I think we need to wrap it up, but let's thank both our speakers again.
You want to meet right away?
Yes, I was just actually
Happy New Year.
thinking about talking to
We meeting? Yes, we are, yes, we are. We have time to get a coffee? That would be good. Where are we?
I thought you just said in your talk that it doesn't really matter.
You've already fixed it up with.
Just for the segregation purposes. So if you have it rather than one peak, it smooths it out. It's not really more, but then look at the difference really like in another. But you're producing it from scratch.
Okay, yeah, there's I'll stop by. Alright, so how about I send you, well, I have your email, how about,
Going back, and that's something that we
so I guess exactly